Hi everyone, I am Tuafong. It's my pleasure to present our work. Let's begin with the introduction. Autonomous systems need to process large-scale, sparse, and irregular point clouds with limited computational resources. Therefore, it is crucial to develop effective and efficient LiDAR perception methods. Existing 3D methods can be inefficient or have performance limitations due to various reasons. Recently, there has been a growing trend of using large kernels. Large kernels gain larger receptive fields, thus increasing performance but also significantly increasing the computational burden. This is especially pronounced in 3D kernels. As shown in the table, parameters and flops increase exponentially with the naive increase of kernel sizes. Large Kernel 3D explores large 3D kernels with spatial-wise group convolution to circumvent optimization and efficiency problems caused by naive large 3D kernels. However, it has many redundant model weights during training as it uses the same weights in each spatial group. Its performance drops when scaling up the kernel size over 7x7x7. Our motivation is to pursue an efficient and effective 3D perception model. Our LSK3DNet incorporates spatial-wise dynamic sparsity and channel-wise weight selection to achieve this motivation. SDS enlarges 3D kernels and reduces model parameters by learning sparse 3D kernels from scratch. CWS increases the model width and learns channel-wise importance during training, resulting in accelerated inference by pruning redundant channels. As shown, SDS can prune 3D kernels to remove redundant weights, while CWS can eliminate redundant channels in an online manner. LSK3DNet benefits from expanded width to achieve enhanced performance but maintains the original model size during inference. In contrast to large kernel 3D, we employ dynamic sparsity training within each spatial group. As shown in the figure, we initialize the sparse large kernel within the spatial group with a sparsity of S. Here 21 weights are activated in one group. Then, at a fixed adaptation frequency, we discard weights with the lowest magnitude and randomly activate the same number of weights. This approach enables us to learn a sparse 3D large kernel from scratch and discard redundant model weights. SDS incorporates two essential components, sparse kernel initialization and sparse weight pruning and growth. In sparse kernel initialization, M is a binary mask generated by ERK-based methods. M is related to kernel size and model width. Then, sparse weights WS are initialized with the shown formula. During training, at regular intervals determined by adaptation frequency, the adjustable weights in the kernels are modified through sparse weight pruning and growth. This process can be achieved using the shown formulations. Previous 2D large sparse kernels followed a regime of use sparse groups, expand more, which led to increased model size. To address this problem, we propose channel-wise weight selection. CWS consists of two steps, channel sorting and selection. During training, CWS performs sorting with the sorting frequency of FS and executes sorting and selection during validation. During training, the expanded model can directly supervise the whole training process. With selected important D-dimensional channels, the model can maintain the original size during inference. As shown, LSK3DNet has a larger effective receptive field size than the baseline. Additionally, to enhance the comprehension of learned kernels, we also offer kernel visualization, providing insights into sparse training. Black areas indicate positions with weight values of 0. Our method demonstrates a notable 2.7% improvement while simultaneously reducing the model size and computing operations by 60%. Our method achieves better performance compared to state-of-the-art methods on several benchmark datasets. We surpass the performance of TUDPASS by 2.7% despite having a smaller model size. Our method also outperforms competitors on both the Semantic Kitty multi-skin test and the ScanNet V2 test, including the prior 3D large kernel method of large kernel 3D. Our method also outperforms Sphere-Former on the new scenes validation set and large kernel 3D on Kitty. That's all. Thank you for watching.